Hello and welcome to our lecture on integrals resulting in inverse trig functions. So we're going to work with this table of 3 rules in this section. We're not going to get too deeply into how these rules are developed in Calculus 1, but a brief outline of how that would take place is take for instance this one here. You would set y is equal to the inverse sine of x over a, and then you would develop the form of the derivative, doing some substitutions along the way from the Pythagorean identity, which says the cosine squared plus the sine squared is equal to 1. And once you get through this whole process, you end up showing that this relationship is true. So we're not going to get into that right now, but we are going to just jump in and use these 3 rules here in this section. So I will point out that there is a notation equivalency here. The arc sine means the inverse sine and so forth, with the cosine and the tangent as well. So between books and teachers, you'll get a preference on one or the other of these notations. Our homework grading system here will take either one. So the other thing I want to point out that there are 6 trig functions, as we well know, but there are only 3 integration formulas. The other 3 are just negative versions of these 3, so you really end up with only these 3 showing up. All right? So these are the rules that we're going to be working with. So example 1, my integral looks like this, which is the form of the inverse sine. So my integral similarities, I see the radical in the denominator, the constant squared, the x term squared. I know I'm going to end up with an inverse sine. So first I'm going to say this is equivalent to 6 on the outside of the integral. Then I'm going to say 1 over square root of 2 squared, 5x squared. And then I'm going to put my dx over here, and I'm going to set up my u substitution. So I'm going to say that a, my constant a, here is 2. I'm going to say that u is 5x. Then I need du, so du would be 5 dx. But looking over here at my integral, I have just dx, so I want to say 1/5 du is equal to dx. So now let's do our substitutions. My u is going to be 5x, and my dx is going to be 1/5 du. I don't need to do any substituting with the constants. So I'm going to take my 1/5 out with the 6. So that'll be 1/5 times 6. That's 6/5. And then I'm going to have my du in the numerator. That's part of the 1/5 du. And then in the denominator, I'll have 2 squared minus u squared. All right, so now I've got it looking like this, and I want to then go ahead and substitute the u and the a in the final result. So that'll give me the inverse sine. I'm going to put the 6/5 out front. Then I've got u, which we said was 5x. That's this here. Then the absolute value of a, well, that would just be 2, so we don't need the absolute value bars. And then plus c. So this is actually just the only thing we need to do, just substitute those in there, and then we're finished. So this one is complete. So example 2 has the same form. So we're going to do something very similar. So first I'm going to rewrite my integral. Then I'm going to notice that a is 2. This is your a. that u is 3x, which would make du 3dx. And then I'm going to also notice that I don't have the 3 with the dx, so I need to divide out the 3 to get just dx. All right, so those are going to be my substitutions. So now I go head over to the integral, and I can see this is going to be u, a is already in it, and dx is going to be 1/3 du. Okay, so now I go ahead and set up the integral in terms of u, and I put my 1/3 out front, my a squared, my u here, and then du. So now I've got it set up like this. You can always put the du on the top to make it look exactly like that. And then it's just a question of substituting u and a into the inverse sign. All right, so I've got a 1/3 out front, which I put here. My u is 3x. My a is 2. And then I have my plus c. All right, so this would be what I'm looking for here. Okay, so now we're going to evaluate a definite integral. I know it's a definite integral because I have values here on the lower limit and the upper limit of integration. So I'm going to end up with a number as my answer. So now I compare the form here, and I notice that everything looks the same except the variable is x here instead of u, dx, see right there. So I don't need to perform any u substitution here. I can just replace x with u, and then I've got my integral. So I can say that I've got the inverse sine of x over 1, a is just 1, evaluated between 0 and 1/2. All right, so that means I've got the inverse sine of 1/2 minus the inverse sine of 0. So what that means is that what is the angle who has a sine of 1/2? Now, when you're evaluating inverse trig functions, especially, we have to be careful of the domain. So the domain is between negative pi over 2 and pi over 2 for the inverse sine function. So here we know that pi over 6 has a sine of 1/2 and 0 has a sine of 0. So this one is pi over 6. This one is 0. So pi over 6 minus 0 is just pi over 6. So that's what we're looking for. This one wasn't too bad at all. So let's do another one like that for practice. So I'm going to notice that I've got the same setup here. So a would be 1 again, u would be x, so I can go directly to my inverse sine result. So I say that the integral equals the inverse sine of x over 1, a is 1, evaluated between 0 and root 3 over 2, radical 3 over 2. So that's the inverse sine of radical 3 over 2 minus the inverse sine of 0. All right, so then we think about where that occurs. So the angle whose sine is radical 3 over 2 between negative pi over 2 and pi over 2 would be pi over 3. And the angle whose sine is 0 would be 0. So we've got these two angles. So that's pi over 3 minus 0. So our result is pi over 3. Okay? So now I'm working with a different form. I don't have the radical in the denominator, so it closely resembles this form, which leads you to an inverse tangent. So now I'm going to write it a little differently. I'm going to say I have the integral of 1 over 1 squared plus 2x squared dx. So I can see that a is 1. Then I would say u is 2x. du is 2 dx. Then I look over here and I see I have only 1 dx, so I'm going to divide by 2. So I have 1/2 du is equal to dx. So the things I want to substitute are the u would go there, and right here, the 1/2 du. So now I rewrite that. I put the 1/2 in front of the integral, put the du on top. So then I've got 1 squared plus u squared. All right, so now it looks like this over here, and I can go ahead and set my answer up just in that form. So I've got 1/2, then I have 1 over a is 1, then I have the inverse tangent of u, which is 2x, over a, which we said was 1, and then plus c. So just cleaning it up a little bit, I have 1/2 inverse tangent of 2x plus c. So we're still working with the inverse tangent rule again, so no radical. So first I'm going to set it up a little differently like we've been doing. So this way I can see that a would be 5. This is a. Then u would be 2x. du would be 2 dx. And then I look and see if I have the 2 with the dx. So that's a no. So I have 1/2 du is equal to dx. Right, then I go back over here and I can see that u is here. dx is 1/2 du. So now I put the 1/2 in front of the integral. Then I've got 1 over 5 squared, which just stays like that. This becomes u squared. And then du goes on the top. Now it looks like this. So I can just go ahead and put everything in the right place now. So this is equal to 1/2 times 1 over a is 5, times the inverse tangent of u over a, u is 2x, a is 5, plus c. So just multiplying the constants in front, I'll get 1/10 inverse tangent of 2x over 5 plus c. So this is my result. Okay, so we're going to do another one similar to that. So first I set it up. So I've got 1 over 3 squared plus x squared, and then the dx over here. So I can see that a is equal to 3, and then u is just dx. So really, this substitution is optional. du is equal to dx, and I don't have a constant to deal with here. So now I can just say that u would go here, du would go here, and this is a. So this one is a little simpler. So I've got the integral of 1 over 3 squared, u squared, du. And I can put the du on top. So since we're beginners at that, we're just trying to make this look as much like this as possible so it's clear where things get substituted. So now, doing my substitutions, I know A is 3, so I've got 1 over 3. Then the inverse tangent of U over A. U is just X. A is 3 plus C. So on this one, we really didn't need to change variables, but we're just trying to be consistent until we get the hang of this. So this is your result here. Okay, so here's a definite integral. So notice the form of this is very similar to this. So A is 1. And then let's try doing this without changing the variable, since X and U we can treat the same way. So everywhere I have a U here is going to be an X. Okay, so I've got the integral between radical 3 over 3 and radical 3 of dx over 1 plus x squared is 1 over a, which is 1, inverse tangent of u over a, so that's x over 1, evaluated. We don't need to write the c when we're evaluating the definite integral, because they'll cancel out when we do the subtraction. All right, so that's just the inverse tangent of x evaluated between root 3 over 3 and root 3. All right, so now subbing in, I've got the inverse tangent of radical 3 minus the inverse tangent of radical 3 over 3. All right, so since we're talking about an inverse tangent, it also has a domain restriction from here to here. Okay, so that means in that region there, the angle whose tangent is radical 3 would be the angle who had radical 3 over 2 divided by 1/2. Sine would be the numerator, cosine would be the denominator. All right, so I know that if I have a positive tangent, that means I've got a sine here of radical 3 over 2 and a cosine of 1/2 at pi over 3. Okay, so this angle is pi over 3. Now let's think about this tangent here. So radical 3 over 3 is another way of writing. If we unrationalize that, so to speak, we can see that this is 3 divided by 3 radical 3, which is 1 over radical 3. So that means my radical 3 was in the denominator this time, and my 1/2 was in the numerator. So these 2's always cancel out. That's how we know this. So this is my sine. This is my cosine. So my sine is now 1/2, and my cosine is radical 3 over 2. So I'm here at pi over 6. So this one's pi over 6. All right, so now let's perform that subtraction. So I've got pi over 3 minus pi over 6. So that's 2 pi over 6 minus 1 pi over 6. So the answer is pi over 6. So here I have another similar problem. I'm evaluating a definite integral. But here I've got a 4, so that's going to make my a equal to 2. But my x isn't a function right in here. It's just x, so we can just replace u with x. Okay? So I've got the integral between 0 and 2 of dx over 2 squared plus x squared. All right, so we said a was 2. So just subbing in, I've got 1 over 2 inverse tangent of x over 2, evaluated between 0 and 2. Okay, so now I can say I've got 1/2 times the inverse tangent of 2 over 2 minus the inverse tangent of 0 over 2. So what I did there was I substituted 2 in for x and 0 in for x. So that's equal to 1/2 the inverse tangent of 1 minus the inverse tangent of 0. All right? So now I look at my domain for the inverse tangent function. So the angle whose tangent is +1 would have to be pi over 4, where the sine and the cosine have the same value. So I've got 1/2 pi over 4 so far, minus the angle whose tangent is 0 would have to be 0 radians or 0 degrees, where the sine over the cosine is 0. So that gives me 1/2 of pi over 4, which is pi over 8. Okay, now we're going to switch it up a little. So I've got this definite integral here, and I'm going to do some u substitution. So this is a little bit of a departure from what we did on the other examples, but this fits in okay in this section. So the rule I'm going to be using is the derivative of the inverse cosecant of x is this form right here. And I can see that I've got that form in the denominator right here. I've also got the negative here. All right, so what I can see that if I choose u equal to, let's just write this out. If I choose u is equal to the cosecant, the inverse cosecant of x, then du is equal to -1 over x radical x squared minus 1 dx. Now what we can see going on here is if I split this up a little bit, I've got the cosecant, the inverse cosecant of x. Okay, I've got a 2 I can stick out front there, and I'm going to separate off the negative and the x radical x squared minus 1 dx. All right, so this here is still the same as this here, but I can clearly see the setup here that u is here and du is right here. So this is u, this is du. Okay, I know how to integrate something like that, but I have to be careful. I've got these two limits of integration here, which I now have to put in terms of u. So u, if x is 2, I'd have cosecant, inverse cosecant of 2. So that's the angle whose inverse sine is the reciprocal of that, 1/2. And of course, I always have to remember my domain is restricted to this here region. So the angle whose sine is 1/2 there would be pi over 6. So my upper limit here in terms of u is going to have to be pi over 6. Now for my lower limit of integration, I've got u is equal to the inverse cosecant. So I'm substituting radical 2 in for x now to find out what u would be. So that means I'm looking for the angle whose inverse, the angle whose got a sine of 1 over radical 2. So that's the same thing as saying the inverse sine of radical 2 over 2, if we rationalize. All right, so that means I'm talking about an angle of pi over 4, whose sine is radical 2 over 2 positive within this domain of the inverse sine function. So that means my lower limit of integration is pi over 4. So I'm going to put that here in the lower limit of integration. All right, so now I'm ready to go. So I've got u, and then I've got du. And I'm all in terms of u, so I can integrate fully in terms of u. So that's equal to 2, raise it up to 2, divide by 2, evaluated between pi over 4 and pi over 6. Right, these 2's are going to cancel. So I've got u squared evaluated between pi over 4 and pi over 6. So that's equal to pi over 6 squared minus pi over 4 squared. All right, and if I perform that calculation, I'm going to get negative 5 pi squared over 144. Okay, so that's in terms of pi. A decimal approximation, if I just use my calculator, I get 0.34269. So here's your approximate answer. Here's your exact answer. Okay, so let's try this kind of setup one more time here. So I've got a similar situation, except this time it's involving an inverse cotangent. So I'm getting this rule off of our formula sheet for where we take the derivatives of inverse trig functions. So the derivative of the inverse cotangent takes this form here. So I can see I've got that form here, and I have the negative, and then I've got the inverse cotangent part of it. So let's just blow this up so we can see it in that form. Put the 2 out front so that you've got the inverse cotangent. And then you've got the negative 1 over 1 plus x squared, and then the dx. So I've got this here would be my u. So let's set that up. U inverse cotangent of x, which would mean du, according to my rule above, is negative 1 over 1 plus x squared dx. All right. So that means I've got my u first, and then my du. Now I need my limits of integration. So for the upper limit of integration, in terms of x, it's 1. So I would put 1 in here and calculate u. So that would be the inverse cotangent of 1. So that's the angle whose cotangent is 1. So that would be the angle whose sine and cosine within the domain of the inverse cotangent function were both the same number, and that occurs at pi over 4. Only one place. All right, so inverse trig functions are a 1 by 1 function because they have inverses, of course. Now for the lower limit of integration, we've got 0 when it's x, so I put 0 here and I calculate u. So I'm trying to find the angle whose cotangent is 0. All right, so that means we know for cotangent, cosine is in the numerator, sine is in the denominator. So that means my cosine must be 0 in order for the inverse cotangent to be 0. So that's the angle whose cotangent is 0. So that means the cosine must be 0. So that must mean that I'm up here at pi over 2. All right, so I've got pi over 2. Okay, so now I'm going to set it up. So I've got 2, all in terms of u, lower limit of integration, pi over 2, upper limit of integration, pi over 4, then u du. So now I'm going to integrate. So that would be u2 over 2, in between, evaluated between pi over 2 and pi over 4. All right, so my 2's will cancel here. So I'll just get u squared evaluated between pi over 2 and pi over 4. So that's pi over 4 squared minus pi over 2 squared. So that's pi squared over 16 minus pi squared over 4. So that's equal to negative 3 pi squared over 16. So this is my exact answer in terms of pi. So my decimal equivalent, if I plug those into the calculator, I get this decimal approximation. This is an approximate result. And then we're done. Okay, so we can also see problems like this in this group of problem types. And this one is going to take this rule here. All right, so the way that I do this is I split it up and I use substitution. So the methodology will be split it up and use substitution. So what I mean by splitting it up is that I think about what my common denominator idea allows me to do. So if I go backwards with the common denominator idea, I can say I've got 8x over x squared plus 1 plus 1 over x squared plus 1. All right, and you can see that's true because if I added my numerators and put it over one common denominator, I'd get this relationship here. So this is just another way of saying this. All right, so now I can treat these two integrals separately. So I can put an integral right here, an integral symbol right there as well because of my integration properties. All right, and then I could put a dx, of course, which I should have as well. All right, so this is my setup right here. So I'm basically going to do two separate problems and then combine them in the end. All right, so we'll put the one integral of 1 over x squared plus 1 dx on this side, and then we'll put the integral 8x over x squared plus 1 dx on this side. All right, so now let's go ahead and do the one on the left first. So this one is going to be an ln. And that's because if I set u is equal to x squared plus 1, du would be 2x dx. Right, so I have an 8 out there, so I can say that 4 du is equal to 8x dx. All right, so now I can do some substitution. So if I break it up, I can see that this part here is 1 over u, and this part here is 4 du. So what I really am going to evaluate is 4 times the integral of 1 over u du. Right, so we know that that's equal to 4 times the natural log of u, absolute value bars, of course, plus c. All right, so that's my evaluated integral. All right, so that's my antiderivative, as more correctly said. So now I can say that's equal to 4 times the natural log, putting u back in. X squared plus 1 is u. X squared plus 1 is u plus c. So this is my left piece of it. And now let's do the right piece. So to do the right piece, I'm going to use this setup over here. So I can see that this would be my u squared, so we can put it in the other order. This is the same thing as the integral of 1 over 1 squared plus x squared. Right, so that means a would be 1 and u would be x. Okay, so this is dx. So now I don't really have to do any, I can just go ahead and substitute x directly into the formula right here for u. So a would be 1, u would be x, a would be 1, and I'd have it. So this is 1 over 1 inverse tangent x over 1 plus c. So that's equal to the inverse tangent of x, just x, plus c. All right, so now I have the other piece of it. So now my final answer would be the sum of those two pieces. So this is my original integral that I'm trying to figure out the answer to, and it turns out it's the sum of these two pieces. So I only need one c, so I'll put that on the end. So that c is essentially a combined c. All right, so this is my answer. All right, so the rules help with these, finding the antiderivatives to some of these pretty complex things, which would otherwise be pretty hard to figure out. Okay, here's our last example. So this is a little bit different because we have a larger power here, and we've got some power of x in the numerator. So, but we do notice here that we've got the radical in the denominator, the minus, and that both of these two terms can be written as squares so that we can utilize this setup here, which will result in an inverse sine function. So the way I would break up this integral, I would say I've got 1 over the square root of 1 squared minus x to the 4th squared, because 2 times 4 is 8. And then over here I've got the x cubed dx. So that way I'm going to write it out. I'm going to say a is 1. All right, so a is 1. Then u would be x to the 4th, which means du would be 4x cubed dx. And then 1/4 du would be x cubed dx, which is what I need. So I've got u here. This is your a. And this over here is 1/4 du. All right, so now I can set my 1/4 outside the integral. I could put my du in the numerator, and then my square root of a squared minus u squared in the denominator. All right, so now I can go ahead and write out my right-hand side of the rule here by substituting u and a into the inverse sign. So I've got 1/4 inverse sine. U, we said, was x to the 4th. A is 1. Plus c. So that's just equal to 1/4 inverse sine x to the 4th plus c. And that's all there is to it. Okay, so that wraps up our example problems for our section on integrals resulting in inverse trig functions.